Let's take a look at another continuous random distribution, which is called the normal distribution. So far in the course we've talked about this somewhat, but now we're going to go into a lot more detail about it. This is a very, very important concept, as the normal distribution will be used throughout the rest of the course quite heavily. So let's talk about it. A normal distribution is one that has a bell-shaped curve, and it's going to look something like this. So characteristics that we look for are that bell-shaped curve, and a normal distribution is always going to be symmetric about its mean. So the mean will be right here in the center. The mode will be equal to that mean, which will also be equal to the median. And if we think of the entire area under all of the curve as 100%, then the symmetry will tell us that 50% of that area must fall to the left and 50% must fall to the right. And the shape of a normal distribution is determined by two characteristics of that distribution: the mean and the standard deviation define the shape of our normal curve. So in the case of a distribution with a relatively small standard deviation, it's going to look something like this. So a smaller standard deviation would tend to have a higher peak and steeper sides, as more of the records are concentrated in the middle, whereas a distribution with a larger standard deviation might look something like this. So it still has the bell-shaped curve here, all of the characteristics still hold, but because that standard deviation is larger, this distribution has a lower peak, and more of that peak area is now found in the tails. We'll now talk about a specialized version of this distribution, which is called the standardized normal distribution. And let me go ahead and sketch a distribution over here. And just for the sake of illustration, let's go ahead and make a few marks on the x-axis. So I'm going to make one mark right there in the middle that will represent the mean of this distribution, and I'm just going to put 1, 2, 3 marks to the right, and we're going to let each one of those marks be one standard deviation higher than the previous one. So the mean plus 1 standard deviation, and the mean plus 2 standard deviations, finally the mean plus 3 standard deviations. And because of the symmetry, we'll do that same thing on the left side of the distribution: mu minus 1 standard deviation, mu minus 2 standard deviation, and finally mu minus 3 standard deviations. And let's go ahead and just put a couple sample numbers with this distribution. So let's say we're looking at a survey of heights, and we'll say that the mean turned out to be 170 centimeters with a standard deviation of 10 centimeters. And then a scenario that we may be asked to solve for would be to come up with a probability that falls between two specific x values from this distribution. So an x value is going to be one individual height of one element from this distribution. And in describing a probability, we will start with a lower bound and an upper bound, and we will use those boundaries to shade in the area that we're interested in describing. We'll go ahead and illustrate that on our first exercise, but for now we're going to talk about the empirical rule. And the empirical rule is a very handy tool, and what it says is that if we look at the area that falls between exactly one standard deviation below a mean and one standard deviation above a mean, we can say that that amount of area is 68.26% of the entire 100%. Likewise, if we expand those boundaries to two standard deviations above and below, we can then say that 95.44% of all randomly selected x values will fall within that range of plus or minus two standard deviations. And then finally, at plus or minus 3 standard deviations, we could expect 99.73% of all values to fall. So let's go ahead and write our x numbers on this scale. Our x numbers refer to the mean of 170, standard deviation of 10. So the mean is 170. One standard deviation above 170 is 180. Two standard deviations above 190 and 200. And likewise, one standard deviation below, two standard deviation below, and three standard deviations below. And we've now labeled an x-axis for this distribution. Let's go ahead and convert these values over to standardized values. So whenever we talk about the standardized normal distribution, we are going to write the number of standard deviations away from the mean that a specific x value falls. So for example, an x value equal to 170 would fall 0 standard deviations away from the mean. So therefore its z-score would be 0. An x score of 180 would fall exactly 1 standard deviation above the mean, and therefore its z-value is 1. Likewise, a value 2 standard deviations above the mean, which we could compute to be 190 in this case, would have a z-score of 2. 3 would correspond to an x value of 200, and on the negative side, -1, -2, and -3 z-scores. So the easiest way to think of a z-score is just simply, for a given value, how many standard deviations above or below the mean does that value fall? Okay, let's take a look briefly at a very important tool that we're going to use, which is the cumulative areas under the standard normal curve, more commonly called the z-chart or the z-table. And with this table, you notice that it has two sides to it. Here we're looking at the negative side. This side of the chart provides areas that correspond to every z-value that falls below 0. And if we turn that chart over, we're now looking at the positive side of the z-chart, and this gives us areas corresponding to every z-value that is equal to or greater than 0. All right, let's take a look at a few sample exercise problems. For our first problem, we're going to see what we can do to answer these questions. Let's first go ahead and read the question thoroughly. Here we're told that the average American male adult is 5 feet 9 inches tall, assuming that the heights are normally distributed with a standard deviation of 3 inches in answering the following questions. So, first thing I'm going to point out here is that what's being referenced is the average American male adult. And by this, I know that I'm looking at a population measurement as opposed to a sample measurement. Because we're looking at every average American male adult, that tells me that this is a population rather than looking at a random sample of that population. So, and the second thing that I want to point out is that we are told that the values in this distribution are normally distributed. So that allows us to use the normal distribution and z-chart to solve this problem. So let's look at part A here. What is the probability that an adult male is taller than 6 feet? So first thing I always like to do on a problem like this is to pull out all of the givens that I have to work with. And here we're told that the mean is 5 foot 9 inches, and we have a standard deviation equal to 3 inches. So with that being noted, we're ready to proceed. First question asks us, what is the probability that an adult male is taller than 6 feet? So first thing I want to do is sketch out my distribution here and go ahead and mark the mean point on that. I'll label this as the x-axis, and what the question's asking me is what is the probability that an average American male adult has a height that is taller or greater than 6 feet. So that's what I need to solve for. So in order to do that, the first thing we're going to do is we're going to take this specific x value, 6 feet, and let's go ahead and draw it on our distribution. 6 feet 0 inches, and because I'm interested in the area greater than that value, I'll shade all the area to the right of that, and once I'm able to solve for this area, that will be the answer to this part of the question. So in order to do that, what we're going to do is we're going to convert this specific x value over to a z value, and the formula that we want to use for that is z is equal to x minus mu divided by standard deviation. So intuitively, this says that the z number is going to be how many standard deviation units above or below the mean that my particular x value falls. So in this case, we have 6 foot minus 5 foot 9 divided by 3 inches. This works out to 3 inches divided by 3 inches, and I'm going to write that with 2 decimal points, so our relative z number is z greater than 1.00 positive. I'll go ahead and note that on the drawing here, and now what we're going to do is we're going to find the area that corresponds to this exact z number, which we know this z number corresponds to this exact x value. So one thing that you always want to remember is that the z-chart areas are given to the left of each of the respective z values that you might look up. So in our case, let's go back to that z-chart, and the z number of 1.00, I'm going to go to my left index, 1.0. To that, I'm going to add 0.00, so lining that row and column up gives me an area to the left of 0.8413. So what we've just found is that the area to the left of the value that is of interest is 84.13%. However, we're interested in the area to the right of that, so therefore we're going to simply subtract that value from 1, and the answer to this question then is the probability that an adult male is taller than 6 feet is 15.87%. All right, good work on that. Let's move right along to part B. And for part B, the question is asking what is the probability that an adult male is shorter than 5 feet. So why don't we go ahead and sketch that out first of all. And the mean, always going to be 5'9", and 5 foot then is going to be quite a ways towards the left end of the distribution. So 5'0", we'll put that here. Let's label this as the x-axis, and our first step then is going to be to convert our x value over to a z value. And the x value that we're interested in is 5'0". So 5'0" minus the mean 5'9" divided by standard deviation, which is equal to -9 inches divided by 3 inches, or a value of -3.00. So our corresponding z value to x equals to 5.0 is -3.00. So let's go ahead and write that out in a probability statement. The probability that x is less than 5 foot is equal to the probability that z is less than -3.00, and I'll go ahead and shade in the area I'm interested in, less than this time, so we're now interested in the area to the left of that z value, and I'll go to my negative side of my z chart and I'll look up -3.0, add to that 0.00, line those up, and we then get an area to the left, which in this case is the answer to our question, of 0.00135, or approximately 1/10 of 1%. So a very small probability to randomly select an element of this distribution and have it be 5 feet or less. All right, moving on to part C. Thus far, we've looked at a configuration of x value or greater than, an x value or less than. Let's look at the third possible configuration now, which is the area between two x values. So looking back at our exercise, what is the probability of an adult male being between 5'6" and 5'10". So in this case, we now have two x values to work with. So let me go ahead and sketch that out real quick. And 5'9" is our mean. Our lower x value is 5'6", and our upper x value is 5 feet 10. So we'll label these as so. That's my x-axis, and to solve this problem, we're going to need to come up with the area of that normal distribution that falls between those two values. And First thing we're going to do, just like we did prior to this, is to calculate the corresponding z values. What's different now is because we have two x values, we need to compute a corresponding z value for each of those x values. So we'll go ahead and say that z lower is equal to x minus the mean divided by the standard deviation. So that's negative 3 inches divided by 3 inches, or negative 1.00. Likewise, the upper value, 5'10", when put through the z formula, is going to give us a value of positive 1 inch divided by 3 inches, or positive 0.33. And I'll go ahead and write this probability statement out. The probability that 5'6" is less than or equal to x, which is less than or equal to 5'10", is equal to the probability that z is between negative 1 and 0.33 positive. So in order to solve this part C problem, let's go ahead and come up with both of those corresponding areas. So first thing we'll do is look up negative 1.00. Negative 1.0 in the 0 column is 0.1587. And likewise, positive 0.33 is a zero number. We'll go to the 0.3 row. The 0.03 column, adding those two together gives me 0.33, and the corresponding area to the left of 0.33 is 0.6293. So I'll jot that down here. And finally, the last thing we need to do here is figure out how much area lies between those two values, and that is going to be the larger value minus the smaller value of the area. So the larger area is 0.6293. That represents everything to the left of our upper value of interest, as well as everything below our lower boundary of interest. So what we're going to do is just subtract the tail area that we don't want, which we know to be 15.87%, and in doing that math, 47.06% of males can be expected to be between 5'6" inches and 5'10" inches. Good job. Let's look at question D. Question D asks us, what is the probability an adult male is no more than 6 feet tall? So we'll go ahead and sketch this out. Here's my mean, 5'9", and in this case, the x value of interest is 6 foot. The statement says no more than 6 foot, so therefore we're interested in everything that would measure 6 feet or less. And I'll go ahead and calculate the z value for that. Z is equal to 6 feet minus 5'9" inches divided by 3 inches. 3 inches divided by 3 inches is 1.00 positive. So my corresponding z number is 1.00 positive. So I can now write this out as the probability of x being less than 6 foot is equal to the probability of z being less than positive 1. and looking up 1.00 in my Z chart, 1.00.8413 is how I come up with that. And because my area of interest is to the left of that X value, the answer to part D is 84.13%. All right, let's finish this exercise up by looking at part E. What is the probability that an adult male is 5 feet 6 inches tall? So part E, let's go ahead and sketch this one out. So an X value of mean 5'9", an X value of 5'6", and this one's kind of a tricky question. One thing you always have to remember is that any continuous variable, the probability of X being equal to one specific value is always 0. If you think of this line as being a mathematical line, by definition then it has a width of 0, so therefore the area contained by this line is also 0. So always remember, the probability of X being equal to one specific value is always 0. All right, good job on that one. Let's look at one more sample question. Here we have exercise number 4 from the exercises pack, and let's see what we have going on here. College presidents receive a housing provision that averages $26,234 annually. Assume that a normal distribution applies and that the standard deviation is $5,000. So let's go ahead and jot down those relevant givens. The mean is 26,234 with a standard deviation of $5,000. So moving right down here to part A. A asks us what percentage of college presidents receive an annual housing provision, keyword exceeding $35,000 per year. So first thing I want to do is sketch out this distribution. So I'm told that it's normal. That allows me to use this tool on it. And for a mean value, we'll go ahead and transfer the mean down here. We'll label this the x-axis. And part A then wants to know what is the probability that a randomly selected college president would receive an annual housing provision exceeding $35,000 per year. So our X value in part A is 35,000, and we're interested in the area to the right of that value because of the keyword exceeding, greater than. So first step we're going to follow here is to convert this X value over to a Z value. So Z is equal to 35,000 minus the mean, 26,234, divided by the standard deviation. And to solve that, we're going to come up with a value of positive 1.75. So our relevant Z value is positive 1.75. So we know the probability that we're solving for is the same probability that Z would fall below 1.75. So let's head over to our Z chart, positive side, 1.7, and we're going to line that up along the top here with 0.5, 1.75, 0.9599 is the relevant area there. So I'm going to jot that on my distribution here, and again, because we're interested in the area to the right of Z equals to 1.75, what we're going to do is subtract the area to the left from 1, and that's going to give us a final answer of 4.1%. All right, moving down here to part B. Part B wants to know what percentage of college presidents receive an annual housing provision less than, keyword, $20,000 per year. So first thing I'm going to do, sketch that out. My mean always stays the same, 26,234. In this case, however, my X value of interest is $20,000. So that will fall quite a ways to the left of the mean. And the keyword is what's the probability of an annual president's housing allowance being less than $20,000 per year. So what we're going to do now is convert that over to a z value. Z is equal to 20,000 minus 26,234 divided by 1 standard deviation, 5,000. And in solving this, we get negative 6,234 divided by 5,000, which is equal to negative 1.25. And so I can go ahead and write that negative 1.25 here. So I know that this z value is negative 1.25, and the area to the left of that is our area of interest. And I realize now that I didn't draw this very well. This would be closer to here if this were actually drawn to scale. That's no problem, however, so let's just figure out what is the area to the left of z equals negative 1.25. Negative 1.25, 0.1056. 0.1056. So 10.56% is our answer to part B. The techniques that we've looked at so far in the exercises are what I like to refer to as the forward technique of doing this method. And the characteristic of that technique is that we always start with an x value, or an upper and lower x value. We then work that x value into a z value and work that z value into an area, and that area then is the answer to this question. Now let's look at a couple parts of this question where we're going to need to use the backward technique. So what we're going to do here is just take this process and effectively run it backwards. So we're going to start with an area, we're going to work that area over to a z-score, and then we're going to work that z-score back to the x-score, which is going to be the answer to this type of question. So let's take a look at part C, and part C asks us the 10% of college presidents receiving, keyword, the largest provision receive at least what dollar amount? So notice in parts A and B, they asked us to solve for a probability or percentage. So that is one way that I was able to identify this as using the forward technique to solve, whereas now I'm solving for a dollar amount or an x value, and I'm given an area, so therefore I need to use the backward technique on this. So let's go ahead and sketch this graph out. So same normal distribution that we're using here. Got a mean of 26,234. Now the area of interest here is 10%, and based on the keyword the largest, out of this whole 100%, the largest 10% is going to fall on the right hand side of the scale. So I'm going to go ahead and shade this area in, label this as 10%, and what we need to do now is to be able to find the corresponding x value or dollar amount that has exactly 10% to its right. So in order to do that, what we're going to do is we're going to take the z value and we're going to convert it over to an x value. So remembering that a z value is really how many standard deviation units above or below a mean that a given value falls, we're going to start with the mean of our distribution, and we're going to find the z number next. So this can be a little tricky when you're first learning it, but what we're going to do is we're going to take the z-chart and look up this area in the middle of the z-chart or the body of the chart and find what z number corresponds to it. So remembering that the z-chart always gives the area to the left of a z value, we're going to need to look up the z value that has the area of 90% to its left. So because 90% falls on the right side of the distribution, I know that my z number will be a positive z number. So I'll go to the positive side of my z-chart, and I'm just going to roam around in the middle here until I find the one area that is the closest on here to 90%. And it looks like here that's going to be 88.97%. So looking at that row, we have 1.2. Looking at the column, 0.08. 1.2 plus 0.08 is 1.28. So my corresponding z number here is 1.28 positive. I can now say that I want to add to the mean exactly 1.28 standard deviations, and in finishing that math, I have a final value of 32,634. So the answer here would be 32,634. All right, and finally for this exercise and topic, let's look at exercise D. So same configuration here. We're given an area asked to solve for an x value, so that's going to be the technique to use for that will be the backward type technique. We start with an area, work that area over to a z-score, and then work that z-score finally into the x-score that is the answer to this question. So as always, I'll start this off by drawing this distribution, and in this case the specific area of interest is the bottom 2.5%. So bottom tells me I'm on the left side of my graph here, so I'll shade this in, and 2.5% tells me that's the exact area that I want my x value to correspond to. So next step in this process is find the z value that corresponds with that area. So the z value for area 0.0250, and in this case, because this is less than 50% area, it falls on the left half of the distribution, so I know that my z number will be a negative number. So because we're looking up an area, I'll roam around in the middle of the chart here until I find the value that's closest to the corresponding area. In this case, 0.0250 or 2.5% is an exact probability, and I'll work that back to negative 1.96. Negative 1.96 is my z number, and that just leaves me with the conversion from z back to x, or z into x. So I'm going to start with my mean, and that is going to be 26,234. To that, I'm going to add exactly z standard deviations. So I'm going to add negative 1.28 standard deviations, which in this case is $5,000. And in finishing the math up for that, we have a final answer for this question that to be in the bottom 2.5% of housing allowances, you would have an allowance of 16,434 or less. Thanks for watching.